Hello friends, in this video we are going to solve a problem where we have an array and we have to partition it into two halves. So this is the left half, this is the right half, and the condition is that all the elements in the left half of this partition should be less than or equal to all the elements in the right hand side. For example, in this case, this is the array. The original array was 3, 2, 1, 6, 5, 3. We are not allowed to change the order. So we have to just find the partition. And it's given that you will always find a non-empty partition. This is the condition that is given. So you don't have to worry about some corner cases like if it's empty, can it be empty or not. So there will always be at least one element in the left side and right side. So these are non-empty. And the left side should also be the smallest, as small as possible. So for example, this was the original array. If we partition here, are all the elements in the left side less than all the elements in the right side? No. You can see that right side had 1 and this is smaller than 3. So this will not work. So we will extend it. Now we partition here. Now we have 3 and 2. So are all the elements less? No. Again, 3 is more than 1. Now we will try here. Now we have 3, 2, 1 on this side and 6, 5, 3 on other side. Now we see that 3 is less than all the elements, less than or equal to. 2 is less than or equal to all the elements. 1 is less than or equal to all elements. So this satisfies the condition. So we have to just return the length of the left one, that is 3. We can extend it further. Let's say if 3 was this side, instead of here, 3 was here in the original array. Then if we include this 3 also, still it satisfies. But still in that case also we would have taken just these 3. The goal is to find the smallest possible left partition with that condition. Now let's take a formal example. So we have another example. So again, finding the partition, we have to consider all the possibilities. So first partition can be here because it is guaranteed that it will be non-empty. So first, second, third, and so on till here. So what we are checking, that all the elements, so this is left half and this is right half. This L and R have multiple elements. So all the elements here should be less than all elements in the right. That means if the maximum in this part, maximum in this L is less than all the elements should be less, means maximum should also be less. So this is true for all the elements. But if we pick the maximum and just compare the maximum, and if maximum is less than equal to all the elements in R, then all the smaller elements will also be smaller because the maximum itself is smaller, then other elements have to be smaller. And we are also interested in all the elements in the right side. So if we find the minimum here in the right part and all the elements in this side, or precisely if the maximum on this side is less than equal to the minimum on right hand side. So let's say right hand side has 5, 7, 20 and this side has 1, 0, 1, 2, 3. So we are just picking the maximum. If maximum is less than all these smaller elements will be automatically. Similarly, in this side we pick the minimum. If the minimum itself is larger than the maximum on this side, then the larger values on this side will also be larger because minimum itself is larger. So in the right side we are interested in minimum. In the left side we are interested in maximum. So now we have to try all the possibilities. So if we do some brute force, let's start with a brute force. So first we will try here and we have 1 here. We will keep track of maximum. So when we are iterating from left to right, we can keep track of what is the maximum till here. Because whatever is the maximum till here, this is the partition that will represent the whole group. So we will keep the running maximum and compare that with all the elements on the right side. So first iteration it will take n minus 1 time, n minus 1 elements are there. Next time we come here, so we compare if this is more than maximum, then update the maximum. Otherwise the earlier maximum will remain maximum. Again compare that with remaining n minus 2 elements and so on. So it will be n square. But just like we kept track of maximum from here to here, can we keep track of minimum from this side, other side of the array? So in order to do that, we can do the pre-processing. So let's keep two arrays of the same size. So let me rewrite 1 1 1 0 6 10. So from left side it should be maximum, left to right, and minimum will be from right to left. So maximum till here is 1. Maximum till this point is, compare just this one with the existing previous maximum. So 1 and 1, maximum is 1. Till here it's 1. Till here it's 1. Now if we come here, we found a new maximum. So maximum till here is 6. And if we come here further, maximum till here is 10. Similarly, minimum, we start from right. Minimum till this point is 10 itself. And we will use these as the initialization condition also. For maximum, we can initialize the first index with 1. This will be the minimum. And maximum we can initialize with last element, the minimum, sorry. Till here, minimum is minimum of current element and the next element, 10 and 6. So minimum is 6. Now we come here. Minimum of 0 and 6 is 0. Minimum of 0 and 1 is 0. Till here also 0, 0. So here we are coming in right to left and maximum left to right. Now we have all the ingredients. Now we are ready to solve it. So we partition here. First point, this is the first partition. So what we need to check is that maximum till this point, maximum before this should be less than minimum from right end till here, one element next. So maximum till here is this value 1 and minimum here is 0. So is this max less than min or equal to? No, 1. 1 is not less than equal to 0. So we did not find a partition. Let's extend it. We will come here, the next partition. Now again, maximum till here is 1 and minimum in this part is 0 till this point. So again the same condition, not satisfied. We move next. Again we compare 1 and this 0. So if this value is I, this index is I, then this value is I plus 1. So what we are comparing? Maxes. So this is max. You can also write max ARR, max array of I should be less than equal to mins I plus 1. When this condition is satisfied, we stop there. Again not satisfied, we try a new partition. Now it's 1 and 6. Now 1 is less than 6. So this is now valid. So we stop here. This is our final partition. So now we have to just return the length of this. So what is the I here where it was satisfied? 0, 1, 2, 3. So we will return I plus 1 because index starts from 0 and we are including till I. So I plus 1. So now what should be the time complexity here? So for creating this max array, it takes n time. For creating this min, it also takes n time. And then we try for different values of I and stop somewhere before the end. So again maybe worst case n. So some constant time n or O of n. Similarly, space required is we are keeping these auxiliary arrays of the same size. So time is O of n, space is O of n. It's very simple. Now let's write the code for this in C++, Java and Python. So you can go through this question, partition array into disjoint intervals. So I have already discussed this. So we will be using this size multiple times, so better to keep it in a separate variable. Min should be of same size n, and min we are starting from right, so we can initialize it with all the values with n minus 1. Similarly, you can keep a better name. Min ARR would be better. Let's make it. And this is from left to right, so we can initialize with nums 0. And now let's fill the remaining elements. So 0 is already filled and the last one is already filled. So you can do it as per your convenience. You can run two separate loops, one starting from right and one starting from left, but you can do it at once also. You need to just do a little bit of jugglery here. Max ARR of I. So this max ARR we are filling from left to right, so the index will remain I. The previous minimum. So while calculating the maximum for this index, we compare with the previous. What was the previous maximum, or that the previous the max at the previous index is the latest maximum. So we compare that value with nums I. So that's why I am writing max ARR I minus 1, one previous value, and the current num. Now we can do within this loop itself, although we have to fill it from right to left, we can manipulate the index. N minus 1 is the last index. So if here we are 1 denotes second value, so n minus 1 minus I will denote second last value. If you are not finding it comfortable, better to do it in two separate loops. Min ARR n minus I minus 1 this thing. So same way, if we are calculating maximum till let's say this index, then we will compare this nums at this index and max at one previous index, because we are coming from right to left. So the same way we have added 1 here. If you add 1 to it, this 1 will go away. This was minus 1. And nums I minus 1, sorry, the same index, whatever is here. So n minus 1 minus I. So now we have both these arrays filled. So we have done the major part of our work. Now we just need one loop and we are done. So max till I is less than equal to min from I plus 1 till last index. Then we return there itself, we break, or we return I plus 1. Because till I we are including an index starts from 0, so there are I plus 1 elements. And here also you need to return some value, although it will not reach here, since they are saying that it's guaranteed that these will be non-empty. But since the return type is int, you have to return some value, so we will return 0, although this will never be hit. Now let's run this. So this is correct. Let's try this example, the second one. Both answers are correct, so we can submit. And the solution got accepted. So I hope you understood it. Now we will write the same thing in Java, and converting it should be trivial. This should be length. And this will become math.max and math.min. Rest should be fine. Let's see. Nums 0. So okay, some typo. Okay, same thing I had. Now it's correct, so submit. Java solution is also accepted, and now we will finally write in Python. Again, trivial to convert. and the Python solution is also accepted.